All right, so what I want to talk about is the various cloud abstractions and APIs we have in Kubernetes, all the cloud-specific controllers we have, that actually so the cloud-specific controllers we have that interface with the Kubernetes API and the various cloud providers. Then I want to talk about how we're trying to migrate from the kube controller manager, the kube controller manager interfacing out to all the cloud providers into this new model where we have the cloud controller manager that is the only thing in the cluster that talks to the cloud provider. And then I want to talk a little bit about how we're going to migrate from this all the cloud provider code living in tree in case.io/Kubernetes to case.io/Kubernetes, case.io/cloud provider, whatever. And then I'm going to highlight some of the technical debt we have in the project. And then, I want to leave about 20 minutes for questions and discussions. All right, so a large part of what the cloud provider is trying to do is build the right abstractions so that any Kubernetes cluster can run on any cloud. And so today's existing abstractions are with nodes, load balancers, routes, and volumes. So for nodes, you can tell that's probably kind of the most the abstraction that's kind of the most important right now, because every Kubernetes cluster is going to have nodes. And within nodes, we have to worry about the various instance types that cloud providers use, whether they have regions or zones or both. We have to worry about the various address types that nodes have, and then we have to worry about how those nodes are identified, because some providers have uniqueness requirements for names, or they have limitations to how long the node name can be, or just a lot of different things. So we have to make sure that what we set as a standard for provider IDs and whatnot is consistent. So let's talk more about nodes. So I just talked about this. One thing I didn't talk about is node conditions and states. So some providers let you shut down nodes. Some providers let you resize nodes. And then there's various intermediate states between running and terminated. And so we have to ensure that all those conditions and states are captured within the current node API that we have. And then addresses I talked about. So that's internal IPs, external IPs, internal DNS, and all that stuff. And then regions and zones. And then Brendan Burns talked in yesterday's keynote about virtual kubelet. So how do we make sure that we're building this node API in a way where we can support things like virtual kubelet in the future. All right, and load balancers. So load balancer specifically is when you create a service of type load balancer in Kubernetes. It then, if it sees a service of load balancer, it'll then fan out and create all these various load balancer resources. And so for some cloud providers, the load balancer resource is just a single thing that they create. Whereas in other clouds, when you create a load balancer, you're actually creating a resource for the firewalls and the IP addresses, the DNS, and all that stuff. And then various cloud providers will support both a network load balancer and an application load balancer. And so we have to be considerate of that as well. So for routes and IPAM, so some cloud providers have a VPC routing table, and this is kind of when you create a node and then you assign some sort of pod subnet to the node, the route controller is responsible of making sure that the routing table for your cluster is in sync with whatever pod subnet the various nodes have. And then there's the discussion around should the routing in a cluster be overlay or underlay, and that's going to vary a lot on what the cloud provider what the cloud provider is actually set up to do. And then there's also IPAM, which is how those pod subnets are allocated per node. So some providers like to do some providers will allocate that IPAM from some cloud service that they have, or they'll just kind of offload all of that onto the Kubernetes API. So let's talk about various controllers. So for each abstraction, we have a controller, so node controller, which does both lifecycle management and registration. And then there's service controller, routes controller, node IPAM controller, and then there's persistent volume label controller. So node registration. So let's first talk about node registration entry. So entry node registration essentially is the kubelet, because it's cloud provider aware, it builds some sort of node resource, because it's cloud provider aware, it can build the node resource on its own, and then once it has like all the metadata filled in specific to the cloud provider, it'll then send that to the Kube API server, and then it'll be registered with all the data it knows about itself from the cloud provider. And so the outer tree model that we're trying to get to is the kubelet will register itself initially, but it won't fill in any cloud provider information because it actually doesn't know anything about the cloud provider. But then it'll taint itself so that some sort of external controller can see the node with the taint and know to then call out to the various cloud APIs and then fill in the cloud provider specific information about itself. So it's kind of like 2 stages of registration that we now have. Another thing, so that's essentially what node controller is doing. Like on top of registration, it also ensures that like the various things like provider ID, all the various address types, those things are all filled in when the node registers. And not just registration, but like if an existing node has its IP address or whatnot updated, it'll also update the node resource as well. Another thing the node controller does is it'll watch for nodes that get deleted in the cloud, and then it'll make sure that if a node was deleted on the cloud provider, that same node that's corresponding to the node object in Kubernetes is also deleted. So yeah, service controllers, what we talked about earlier, it watches for services of type load balancer, and then it'll then call this method called ensure load balancer, which creates the various cloud resources that specific cloud provider needs for load balancers. Same thing with routes controller. It watches for nodes. It'll check that if it has a pod CIDR allocated, which is the IP addresses that are allocated for pods on that node. And then it'll then check if the VPC routing table for that node exists. And if it doesn't exist, it'll add it. And if there are like access routes or routes for node that were deleted, then it'll make sure the VPC routing table is up to date. Persistent volume label controller, it watches for persistent volumes, and then it ensures that metadata pertaining to that volume on the cloud provider is set. And this is mostly for things like zone and regions that are used for, essentially used for the scheduler to do like affinity rules and then whatnot. Okay, so migration to out-of-tree cloud providers. So in the intro, I show this diagram, which is showing today's existing architecture for cloud providers. And this is where we have the cloud provider compiled into the kubelet and the API server and the kube controller manager, which meant that like all the various components have to have like all the cloud provider libraries and APIs compiled into it. And the model that we're trying to move towards is where the kubelet, the API server, and the controller manager should not know anything about the cloud provider, but we have this new component called the cloud controller manager that knows how to interface with the cloud provider, and it should be the only thing in the cluster that's doing that. And so what we're trying to get at is like, we have the kube controller manager that has both the core controllers, which deal with like pods, nodes, and all that stuff. And then we have specific handful of controllers that are cloud specific and interface with the cloud provider. And so over some amount of releases, what we're trying to get at is like, the kube controller manager should only have the core controllers, and the cloud controller manager should have only the cloud specific controllers. And realistically, so to get from here to here, we can't just like merge a giant PR that just does this. We have to make sure that as we transition, there's a backwards compatible way to flip the switch between what is running the cloud-specific controllers and what is running the core controllers. And so like the Kube controller manager needs to have some sort of way to still connect to the cloud controllers, but we have to be able to turn it on or off depending on what the cluster setup is going to look like. And this is important because, let's say in Kubernetes 1.15, we decide to tell users like by default, the cloud controllers in the Kube controller manager are going to be disabled, and you should run a cloud controller manager in your clusters. And if there's some critical bug in that code path, we need to be able to let users still choose to opt in for the previous architecture so that their production clusters aren't on fire. Okay, so let's talk about volumes. So volumes is a very volumes is still like cloud provider specific, but it's a little bit different from the rest of the cloud provider architecture because there's a separate like plugin, there's a separate directory that is specifically for cloud provider volumes. And so this cloud provider code is not actually embedded into the Kube controller manager, but it's all embedded into the kubelet. And then the kubelet then calls out to these various cloud provider volumes, and then it'll know to like attach, detach volumes and mount them and stuff. And so this is today's architecture where when we build the kubelet, we're building like all of these volume plugins into the kubelet. And this is kind of what CSI is supposed to fix. Instead of adding to this ever-ending list of volume plugins, we're supposed to be using CSI. And so we need to also have a migration path from the kubelet using these volume plugins to the CSI. And similar to the migration for the cloud controller manager, we can't just change the code to do that. We need some sort of like transitional period where we're going from the kubelet doing some sort of like being able to do either the in-tree volume plugin or the CSI plugin. And so SIG Storage wrote a CSI translation library embedded into the in-tree volume plugins that know how to translate a call from the in-tree volume plugin into the CSI driver. And of course, like if there's a bug in the CSI driver, you can set some flag on the kubelet, and then it can kind of skip the CSI transition and fall back to whatever the previous behavior was. And so this allows us to like force users to use the CSI, but also give them a way out if they find that it's causing issues in production. All right, so code migration. So I talked a little bit about this in the intro, but today all the cloud providers live in the main tree under a package, cloud provider providers. And one intermediate step from getting from the in tree to completely out of tree is that we have to stage the cloud providers in the staging directory. And the reason we do this is because we need a way to like, it's essentially for transitional reasons. We can't just like flip the switch and move everything. We have to be mindful of the fact that people depend on this code in production, and so we need to do it in a way that's safe, I guess. And so the biggest challenge from going from here to here is that anything that's staged is actually not allowed to depend on back into the main tree. So like if anything in these directories have a dependency to k.io/Kubernetes, then you're not allowed to actually move it to here. And this is to avoid circular dependencies in the actual in Kubernetes. And so the first step is to actually refactor all of this code here to not depend on the core Kubernetes tree. And so we have an issue open that is listing all those dependencies, and that's kind of where we're at right now. We're just trying to refactor a bunch of code to get rid of this. And then once we do that, then we can move everything to staging, and then we have a publishing system to sync everything that's in staging to the out of tree repos. And then once we know that this works, then we can just get rid of the staging repos and go completely out of tree. And so, yeah, so the reason why we need staging, again, is because we need a way to compile both the Kube Controller Manager and the Cloud Controller Manager in a single place. And so what this allows us to do is the Kube Controller Manager can still import the various cloud provider repos from the main tree, but then the Cloud Controller Manager can sync all the various cloud providers from the actual out-of-tree repos. And so, yeah, I showed this earlier. This is essentially like, so yeah, the Kube Controller Manager, again, it's calling all the entry stuff from staging, and then the Cloud Controller Manager is calling all the it's interfacing out to the cloud provider, but it should be imported from all the various out-of-tree repos. And because we're going to be having this, because we're going to have all the cloud providers in staging for some period of time, we can do this mechanism of having the Kube Controller Manager have some kind of backdoor into the cloud controllers. And so, yeah, this is the end goal. We want all the cloud providers to be out of tree. Out of tree just meaning like it's not in the core Kubernetes repo. And then the goal here is that these are independent modules that can be developed independent from the Kubernetes release. And then the various cloud providers can publish their own releases that can be kind of added onto any Kubernetes cluster to kind of add all those cloud provider features. Okay, so technical debt. So this section, I just want to like highlight some of the issues we have right now in terms of cloud providers. And so like, if you look at the kubelet, there's a lot of code like this where we're saying, like, do this thing if, I replaced the actual cloud provider name with foobar because I don't want to like, call out any providers, but like, there's a lot of like, if this cloud provider, then do this. And this puts us in a tough spot because we actually can't deprecate the providers in the kubelet until this is gone. But this is such a critical piece of the kubelet for this cloud provider. And so like, this is a tough spot to be in. So we have to like think about like how to get rid of this code without breaking anyone's production cluster. And that's part of that's a lot of the reason why like this kind of effort takes a long time. Yeah, likewise, there's like, if it's this provider, set this node condition, otherwise like, okay, so for this case, it's when the node registers, the node is not added to the VPC routing table. And so there needs to be a condition on the node to ensure that nothing is scheduled on the node prior to that the routing table being updated. So what happens is when the node registers, the first thing we do is we give it a condition, no route created, and then the route controller, once it adds that node's route to the VPC routing table, it then removes this condition. But ideally, like we shouldn't have these if statements in the code base. Everything should be like broken out, and the kubelet itself should not actually be aware that this provider has this special rule. And yeah, same thing. There's a lot of this. There's just, if you look at the code base, there's just a lot of like this kind of code. And essentially, we're trying to get rid of any code in Kubernetes that is doing like these very specific edge cases for cloud providers. All right, so I think we have about 15 minutes. So I wanted to open it up to any questions or discussions around the SIG. Questions? All right. Okay.
Does it work? You've mentioned that Cloud Controller makes sure that nodes has all the readiness conditions, label stains, etc. So is it like feasible for a Cloud Controller to go a step further and create or delete a node if it is requested of it? Is it feasible, like, to do it this way, or?
For the controller. Sorry, we're having issues with the mic.
Okay.
All right. Okay. One more time.
Anyway, so the question was, is it feasible to like use this cloud controller to request new nodes instead of just making sure the nodes that register have the right labels, conditions, etc.?
Yeah. I don't think it's not impossible, but I would say like I think that's sort of where the cluster API work is heading, where like we want the cloud controller manager to be, it's mainly just like porting logic out of the kube controller manager, and so like whatever the kube controller manager was doing, we're trying to get the cloud controller manager to do that. And so like I don't foresee in the future the cloud controller manager being able to create nodes.
Well, currently the cluster API is doing that work, right? So it's in another project which is called the cluster API, which is located in the Kubernetes SIG, and I think you can take a look. It includes all kinds of like create the cluster, upgrade the node, delete or create the node, something like that. And I think the CCM is only for the load balancer or some kind of storage stuff.
Yeah. But that's not to say like the cloud controller manager can't call back out to the cluster API, right? So those are feature use cases that we can look at. Cool. All right. Thanks for coming.